everyone. Welcome to week 4, lecture 0 of CS50DC. Before we start today's lecture, I would like to advertise 3 things. The first thing is we have permission now to carry out a hackathon on the 23rd of November, 5 till 10 p.m. So that's going to involve 5 hours of coming into one of our computer labs, doing some very purposeful programming to do with what we're talking about today and what we'll be talking about over the next couple of weeks. We'll be getting in pizzas, we'll put some music on, and hopefully make it quite an enjoyable 5 hours for you. So you're all invited to attend that. I'll be sending out a Google form later on to actually ask you to sign up if you want to attend. So that's the first thing. The second thing I would like to advertise is that on Sunday, period 6, if you have a free Sunday, period 6, Ocean is going to be doing a long presentation for us. And I don't mean long as in it's going to take a long time. He's going to be doing a presentation that we'll put on the CS50DC YouTube channel. It's a theory presentation about floating points. Okay, so if you have interest in that, please come along. It's in A1, period 6 on Sunday. And then the final notice that I've got for you is your deadline for P-Set 1. Your deadline for P-Set 1 we've agreed is next Tuesday, and that will include next Tuesday, so we expect P-Set 1 to be submitted by midnight next Tuesday. And Mataza has uploaded a video on Facebook to show you how to do that, so to how to submit P-Set 1. Okay, any questions about those? Okay, so I'd like to hand over to Ocean for today's lecture.
Where's the freeze button on this?
In the middle.
There you go.
You pressed it twice. Okay, awesome.
Okay, guys. So, if you remember the last lecture, I'm gonna try to pick off where we left off. And in the last lecture that we did, we talked about all these different data types that exist in C, and we also talked about how they're stored in the computer's memory, and we ended by talking about something called overflow, which is one way that a computer can misrepresent data. And just to continue on that, I want to introduce this popular notion that a computer is so much smarter than a human being, that if you want to do some sort of calculation especially, you should hand it over to a computer because it's faster, it's more accurate, and it's just better in every single way. And today I want to sort of challenge this notion, and we did start challenging it when we talked about overflow, how a computer can't actually make mistakes. But today I'm going to talk a little bit about floating point numbers, and of course on Sunday next week I'll talk much more in depth about them, but I will be challenging this notion. So just to begin with, let's type in a very simple program in C, if this computer works. And I'm going to try to demonstrate that a computer can actually be quite imprecise in many ways. So I'm just going to save this as imprecision.c. Awesome. And just as any program, I'm going to start off by including the standard I/O library. And I'm actually not going to include the CS50 library because I don't really need it for today. So int main void, which is hopefully becoming very familiar to you, to type out. And I just want the computer to print out the number 0.1 for me, just to see what happens there. And you'll see why I'm doing this when we do it. So of course we create a string, put in a placeholder for a float, and I'm just going to type in 0.1. I'm actually going to put a new line after that as well. So once I save that, it's green, cool. I'm going to compile that, okay, compile Imprecision. Cool, and now let's just run it to see what the computer returns. And okay, that's what we expected. As we know from our current understanding of mathematics, 0.1 is equal to 0.10, which is equal to 0.1000, an infinite number of zeros afterwards. So we know that's completely correct. But let's just put it to the test a little bit further, and let's say I want it to 10 digits after the decimal point. So I'm just going to run this again, or compile this again rather. This loads, there we go. And run it again. And we can see, it's still completely fine, 0.10000. As long as there's only zeros after that, we're completely fine. And, the computer is in agreement with our understanding of math. So let's just finally just put it to the final test of 100 decimal places, just to see how precise a computer can actually store these numbers. So Let's once again compile this program. Run it again. There we go. We end up getting this weird number over here, because it starts off really, really well, 0.100000000, but we have this 5551, this random kind of string of random numbers in between, and we know for a fact that 0.1 is not equal to that. It's very close to that, but it's not actually equal to that. So by the end of the first half of today's lecture, I want you to understand why this is happening and how this can kind of impact your code. So, since we're talking about the number 0.1, let's really try to understand what this number actually is. And we know that using the decimal system, we can represent it like this. We know that the 0 represents how many 10 to the zeros there are. The 1 represents how many 10 to the minus 1s there are. And just to simplify this, we can write it like this. There are 0 ones, and there are 1 tenths, and then there are 0 hundredths, 0 thousands, etc., etc., etc. And we know if you wanted to figure out the value of this number, what we have to do is simply a bit of math. 0 times 1 plus 1 times a tenth, which we know is 0 plus 0.1, which gives us the answer 0.1. That's completely fine. We understand this number now. And the system works exactly the same for any other number. If it's 0.3, just a 0 times 1 plus 3 times a tenth, which is 0, plus 3 times 0.1, which gives us the value 0.3. So now, let's just get back to the number 0.1 and think about how this number would be represented using a binary system. Because right now, we know that this is using the decimal system, right? And it turns out, it's actually very, very similar. The way to read these numbers and to understand what they represent are very similar. All we simply have to do is change the base to a 2, from a 10 to a 2. So before it was 10 to the 0 and 10 to the minus 1, but now it's simply 2 to the 0 and 2 to the minus 1. It's a base 2 number, hence binary. And just to simplify it, we can say it's 1 and a half, and we have a quarter and 8ths and 16ths afterwards, and which continues forever and ever. And to calculate the value of this, we do exactly the same thing. 0 times 1 plus 1 times a half, which is 0 plus 0.5, which gives us the value 0.5. So we know now that the number 0.1 in binary represents the value 0.5 in decimal. And this subscript 2 and the subscript 10 just means that this number is written in base 2, and this number is written in base 10. So that's all that means. So now we know what the number 0.1 in binary translates to in decimal. But now let's try to figure out the question that we began with, the number 0.1 in decimal into binary. How does that conversion work? Well, we use the exact same system as we did before. We put in all these half, quarter, 8, 16, 32s. And someone did the math for us, and it turns out 0.1 is represented by this number in binary. 0.0001100110011 forever and ever and ever. And you may be wondering, how can a number recur infinitely? Well, the thing is, this exact same phenomenon can actually be found in decimal numbers as well. So if I asked you to write down the answer to 1 divided by 3, you'd write 0.33333, and it'll go on forever. It'll go on infinitely. In fact, this massive wall can't even store this entire number because it's just going on and on and on and on. And there are an infinite number of digits, or binary digits, or bits that we have to store in a computer's memory. But we know for a fact that a computer doesn't have an infinite amount of space or an infinite amount of memory. It has a finite amount of memory allocated to each data type. And we know exactly how much, because if we use the program that Murtaza showed us last week, which basically just says print out the size of a float, or how many bytes a floating point number or a float takes up in our memory. And this will return the answer 4, telling us that it takes up 4 bytes. And in our very first lecture of the course, we said 1 byte is 8 bits, hence 4 bytes are 32 bits. So now we know that a floating point number physically takes up 32 bits in a computer's memory. But it turns out it isn't that simple. And this is a diagram that you really shouldn't understand right now, because we haven't talked about it, but this Sunday, or next Sunday rather, I will be dissecting it bit by bit so that you understand what the sign and the exponent are. But there are some other stuff there that we don't really have to worry about for now. But it turns out only 23 bits are actually used to store the significant digits of the number. So we only have 23 digits to store the infinite number that we just saw. And yeah, that's all you need to know for now. So if we try to store this infinite number, which goes on forever and ever and ever, into 23 bits, so let me just visualize this. I don't know if you guys can see it, but I know you can't. I kind of grayed out this part over here. So the 23rd bit is that, and all of these will be cut off. So what the computer literally would just cut it off, and if you guys saw right there, the 0 actually rounded up to a 1, and the reason that happens is because the computer automatically rounds up the 0, or just rounds up this 1, or rounds up the 0 because of the previous 1 there. So the computer would literally be storing these 23 significant digits in the computer's memory. And so I forgot what my next slide is actually, so I'm just going to have a sneak peek. Yes, this number, it turns out, if represented in decimal form, we actually get this number, which we saw in the very beginning of our lecture today. So we know that up to like 5 decimal places the number is correct, up to 10 it's still correct, but the more and more precision that we try to gain, the more errors that the computer tries to make, or the computer makes for us. And we call this an error related to floating point imprecision, or we can also call it a rounding error, because as we saw here, or as we can see here, it's an infinite number that the computer is trying to store, but it rounds it up to 23 significant digits. So we can also call it a rounding error. But we can see here on the board that this number that we get is actually very, very close to 0.1. It's not quite 0.1, but it's really close to it. And that's why for like 99% of the programs that we're going to write, this is not an issue for us. If you perform math like 0.1 times 10, it's still going to output the number 1 for us. So 0.1 times 1,000, it's still going to output the number 100, which is still correct. Because we simply don't need this level of precision. But as we will see a little bit tomorrow, there are very real scenarios in the world where this has come to harm humanity. So for example, imagine you're someone working at NASA and you're trying to send a shuttle up into space. You do need this level of precision. And if you're trying to do something like that, this system of floating point numbers sometimes doesn't really work. So people have to figure out different ways, which I won't really go into for now. But the thing is, what I want you to take away from today is there are many ways that a computer, or if I just go back to this, there are many ways that a computer isn't actually as smart as a human because of the finite nature of its memory. So if we go back to last week, there's things like overflow and underflow where data can't be represented, or it can be misrepresented. And we also learned today that we can also get something called a rounding error, which will give you a wrong answer if you're working with very, very precise numbers. So whenever you get an error in your program, especially if you're running a very complex program or a very mathematical program, always be sure to account for these types of errors that could happen. Always keep them in the back of your mind and do not fall into these pitfalls. And now, we sort of know what to avoid when we're programming. We know what pitfalls to avoid now. So let's actually get to doing some more programming now. You all have your laptops out, and now I'm going to invite Murtaza up to show you some new constructs which we haven't seen before. So over to you.
Okay, so we're going to take a quick look at some of the programs that we wrote in the previous lectures. This mouse is quite bad. So let's open up something like Fahrenheit.c. Actually, let's not use that one. It's a bit long. We'll go for size of .c. So if we look at this program, we can see that when the compiler compiles it, when we compile this program and run it, essentially what's going to happen is that each of these statements, the print statements, are going to be run one after the other. First this, then this, then this, then this, then this, then this, then this. And that's it. The program's going to end. If we look back now to the algorithms that we talked about at the beginning of the course, like we looked at binary search and we looked at the peanut butter algorithm. The peanut butter algorithm was kind of like this, where it's a sequence of steps that you're going to repeat in order, in a specific order, in the same order every time. You're going to repeat every step. But if we think back to the binary search algorithm, where we split the dictionary in half each time, and Ojin was showing his strength to us, we can see that there are certain conditions where we'll do something different. So we won't always rip the dictionary in half. In some cases, like in case we do find the word, we have a different step. So how do we do that in programming? How do we branch the program? How do we change what we actually do? How do we choose which statements to run? How do we control the flow of the program? Well, let's look at something that some of you might have seen before, called an if statement. I've written a program here that takes an integer from the user, stores it in a variable I, stores it in an integer I, And then we see this statement, if I less than 8, print your number is less than 8, and then printf thank you. So what's happening here is that at the beginning, the first print statement will get run in order. Then this int I equals get int will get run, so the user will be asked for input. Now we have this if statement. And what this if statement is doing is it's going to check this condition. It's going to check I is less than 8. And I is either going to be less than 8 or not be less than 8. So it's either going to be true or false, a Boolean value. So this is a Boolean expression here, I less than 8. And if this is true, all the code that's inside the curly braces is going to run. So this statement is going to run. And then once that's finished, this statement is going to run. So essentially we've created a branch. Part of this program only runs in certain cases. And let's prove that. Let's go ahead and run this program, which is called if1. Please enter a number. Okay, we enter 5, and it tells us that you're... Jesus, it's the wrong if1. If0. We enter 5, and it tells you that your number is less than 8, and then it says thank you. So the program went, int I equals get int. It asked us for an int, and we typed in 5. It went, if this number is less than 8, which it is, 5 is less than 8, do this line, which is just printing out that your number is less than 8. And then it's going to do this line anyway. And to prove that that's only going to happen sometimes, we can just confirm that by running if0 again, and putting in the number 10. It didn't say that your number is less than 8, because the condition was false. So this is a simple case of an if statement. And in fact, if statements can get even more powerful than this. You can create complex behavior, such as this, if we look at if1, which we kind of saw already a little bit. We can have two if statements here. So first this condition will be checked, and if this condition is true, this code will be run. Then this condition will be checked, and if this condition is true, then this code will be run. Let's try this one out. /if_1. Let's try it with a number like 5. And expand the terminal a bit. We can see that it checked the number against 8. It is less than 8, so it said your number is less than 8. And it also checked it against 10, and it is less than 10. So it printed out that your number is less than 10. But then, if we enter a number that's between 8 and 10, maybe, we'll see that only part of this program will run. Let's try entering the number 9. So 9 here is not less than 8, so that this part doesn't run, but it is less than 10, so this part runs. And then the thank you bit, which is hidden by the terminal, runs at the end. So you can have multiple if statements in a sequence to do different things based on different conditions. And you can also link if statements together. What I mean by that is, the only difference between this file and the one we just looked at is this word else here. Now what this is going to mean is that if this condition isn't true, then this condition gets checked. Whereas if this condition is true, this part of the code doesn't run. So it's either going to pick one or the other. It's never going to do both. And let's just confirm that. We will run if2, enter a number. Let's try the number 6. Oh, that's a 5. Your number is less than 8, but it didn't say that your number is less than 10, because once this condition happened, the program doesn't bother checking this condition, because it knows only one of the two is ever going to happen. So that's how you use an else if. And let's just show you that if we put a number that is less than 10, but not less than 8, then only this part of the program runs. So this part is false, so then this condition gets checked, I less than 10, which happens to be true for 9. So this statement, this string gets printed out. One more thing we can do with if statements. We can have a situation where it catches every other condition. So we had if, we had else if, checking another condition, and now we have else, which basically means if none of these other conditions were true, go here. And in this situation, it's checking your number I, checking whether it's less than 8. If it's less than 8, it tells you. If it is 8, it tells you. And if it's not less than 8 and equal to 8, then it must be greater than 8. So we've used that knowledge to say that your number is greater than 8 if the other two aren't true. And let's again run this to show that. Enter a number, let's go for 4. 4, your number is less than 8, thank you, so that's correct. Let's try it with 8, exactly 8. Your number is 8, so as we can see here, it failed this check, but this check was correct, so it did this code. And try with the number 10. Your number is greater than 8. So here we have an if statement which has 3 possible branches, only one of which will run, and the else clause at the end just means any other condition than the ones we've specified. Now, if statements are quite useful because we can branch our program into different paths using them. But there is another form of branching program into different paths. Imagine you had to write a program that does something different for depending on what grade you get in an assignment. So you enter your grade A, B, C, D, E, F, G, U, and it chooses what to do based on that grade. You could say if grade equals A, do this. If grade equals B, do this. If grade equals C, do this. But thankfully, we don't have to do that. There's a way to simplify that because the authors of C included this structure called a switch statement. So what the switch statement will do is it'll take the variable that you give it. In this case, that variable is a character called grade. And it will check it against all these cases. So in case the grade is A, it will do all of this. And then we have to put a break clause here because as you can see there's no curly brackets around it, so it doesn't know where it starts and ends. But we can specify where that case ends by putting in break. So in the case of the grade being A, it'll do a specific thing, it'll print well done. If the case is B, it'll print nice. And default here just means anything else. And it'll print that I know you can do better. So let's see how that works and see that it does work. Switch. Switch 0 it's actually called. What is your grade? Say I got a B on my last assignment. Nice, okay. I had an F on another one before that, and the program is telling me that I know you can do better. So essentially it's checking the grade against all of these cases and doing whatever code is included in that case. What's nice about the switch statement is that you could have multiple cases that correspond to the same code. Because if I typed in my grade with a lowercase a, it wouldn't have worked in the previous one, because here it only checks for exactly this character, a capital A. Whereas in this new program, I've included 2 cases for the same code. So we can stack the cases on top of each other and say, in both the case that it's A or lowercase a, print well done. In both cases that it's B or lowercase b, print nice. And we can just confirm that this one works as intended as well. This is called switch 1. And we will try a lowercase a. And it does that code up there, print well done. So these switch statements are very useful for when you're trying to branch a program based on an input that can be one of a certain number. It can be one of a few different inputs. So in this case, your different inputs are A or B. And then you can have a situation for where it's none of those inputs. And that's kind of it for the branching parts of C. If statements and switch statements. And they are quite powerful because you can check you can start getting more and more advanced conditions. You can start linking conditions together. As we saw with the else statements, you can choose one of many paths for the program. Or you can have various different paths that depend on the condition, like we saw with the 2 if statements, like less than 8 and less than 10. They both ran if you put 5 in. But now we're going to talk about another control flow element in C, which is that of loops, which we've kind of been talking about a little bit in our workshops, and it's kind of the core part of this problem set. Problem set 1 is looping. So let's look at the most basic kind of loop in C, which is called a while loop, and dissect how that works. Imagine we wanted to print all the powers of 2 that are less than 500. Well, what we can do here is create a variable that stores the current power of 2. It starts off at 2 to the power of 0, which is 1, prints that number, and doubles it. And now each time we double it, we want to print it again, right? So we could, in theory, write double it, print it, double it, print it, double it, print it. But as I said in the previous lectures, we can simplify this with a loop, because what's inside this loop is going to keep running in this while loop. It's going to get to the bottom here and go right back to the top and do it again. The only thing is, it will check this condition every time, and it will only continue doing the loop if that condition is true. So at the beginning, current is 1, it'll be less than 500. Then it'll double to 2, it'll still be less than 500, it'll double to 4. It'll keep going until it reaches a point where it's higher than 500, and then the loop will stop and the program will end. So let's take a look at this loop. /while 0. So we got all our powers of 2 that are less than 500. Once it doubled from 256, it became 512. It checked the condition. Is this less than 500? No, it's not, so the loop ended. And we can do some more, we can do something different. We could say, what if we wanted to print, instead of all the powers of 2 that are less than a certain number, what if we wanted to print the first 20 powers of 2? So here we have 2 variables now. We have the current power of 2 and we have an I. I is conventionally used to represent a counter because we're counting the number of powers of 2 that we have. So we'll start with 0, go 1, 2, 3, 4, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So what we have here is, while I is less than 20, print 2 to the power of I equals current. Basically, it's just going to show us that 2 to the power of 0 through 19, what the value of that is. Each time at the end of the loop, we're going to double the current value, and we're going to increment the counter by 1, I plus plus. I equals I plus 1. We're going to increase I by 1 each time the loop runs. So eventually, after it runs 20 times, I will be equal to 20, so the loop will not run anymore. Let's just confirm that one. We should get up to 2 to the power of 19 successfully. So it starts with I equals 0, prints out the power of 2, and keeps going all the way up until it's 2 to the power of 19, which is 524,000. And then it stops, because I is no longer less than 20. The next time it increases I, it would have been 20, and then this condition would be false. And so the program would continue on after the while loop. Since there's no code here, the program just ends after that. But this form of while loop can kind of be simplified, because it's very common in C to use counter variables, to do a certain task a certain number of times. In this case, we've done it 20 times. And this is such a common construct that the authors of C actually included a specific loop for this, a specific loop type for this kind of iteration. So if we compare this program that I've just opened up and this one here, it's almost identical, except in this line here I've used a while loop, and in this line here I've used a for loop. And if we look inside the for loop, we can still see that I less than 20, exactly like we had with the for loop, with the while loop. But what we can also see is this int I equals 0. Well, hang on, in the while loop, that was just the line before. It was exactly the same thing, int I equals 0. Here we've put it inside the for loop. And then this I plus plus here, well yeah, that was over here. That was right there. So the for loop essentially is just a shorthand for the while loop. It has 3 parts. The initialization, which is what is run once at the beginning of the loop. The condition, which is checked every time, just like in a while loop. And the afterthought, which is something that's run at the end. Is run at the end of the loop every time. So if we compare that to our while loop, this thing gets only run once because it's not in the loop. And this thing gets run every time the loop finishes. And this condition here, this expression gets checked every time the loop is about to start. In the for loop, we have exactly the same thing then. This thing gets run once. This thing is run at the end of every iteration, the afterthought. And this thing is checked every time the loop is about to start. So once this is no longer true, just like the while loop, the for loop will stop. Let's just show that. /while, oh no, we're doing for now. exactly the same results. 2 to the power of 0 equals 1, 2 to the power of 1 equals 2. Once this I value here, which is this number, gets to 20, just like with the while loop, the for loop stops. So this is what a for loop is. It's a way of doing things a certain number of times. Usually a for loop is used when you know how many times you're going to do this iteration. Like here, we know we want 20 powers of 2. If we go back to our while 0 file, we don't know how many powers of 2 we want, but we just want them as long as they're less than 500. So it's kind of a different use case. Here we don't know how many we actually want. Whereas with the for loop, or actually you could use the while loop with a counter, which is just exactly the same as a for loop. In the for loop, we know that we're going to do this 20 times. So this is a form of definite iteration where we definitely know how many times we're going to do this. Let's look at another use case for while actually, which is something that you guys are going to be doing in your problem set. Imagine we wanted to get input from a user that matches a certain condition. We could get that int, please enter a number that is less than or equal to 8, and then get this number and store it in I. What we could do is say while I is greater than 8, so while I doesn't match those conditions, print please try again and ask for I again. So essentially it's going to reprompt the user if they get it wrong. And if they still get it wrong, it's going to reprompt them again. And if they still get it wrong, it's going to keep reprompting them until they enter a value of I that does not satisfy this condition, which means it is the right value of I that you want. Then we can continue on with our program. So this is a way of checking user input using a while loop. Let's see how this works. The program is going to ask us to enter a number less than or equal to 8. And let's start by giving it the number 4. That works fine. But let's try giving it a number that is not less than or equal to 8. Please try again. So what happened was, we gave it a value of I, 10, which got stored in the int I. It checked that I is greater than 8, which it is. 10 is greater than 8. So then it ran this code. Please try again. And asked us for another int. So now, it's going to keep asking us for more ints until we give it one that does satisfy its condition. Because once I becomes something that doesn't satisfy this condition, this loop is going to stop running. So essentially here we've asked for input from the user and made sure it satisfies our requirements for that input. And there is one more simplification that C authors have written for us for this use case, which is where you want to potentially do something once, definitely, and then maybe repeat it again and again. Because we want at least one input, but we might need more. This is, they've added something called a do-while loop, which we can again compare side by side to the while-to loop. It's essentially the same. We still have a while, except we start off with a do here. So the while I is greater than 8 is exactly the same as the while I is greater than 8 here, except it appears at the bottom of the loop. And the other thing that's happened is we've gotten rid of the getInt over here, and instead there's only this one in here. So the way this works is, the program's going to start, it's going to do this loop once, and then it's going to check the condition. And then if the condition is true, then it's going to keep repeating it. So it's going to definitely do it at least once. If we go back to the previous while loop here, if this condition is false at the beginning, so if I is already less than 8, then this loop is not going to run even once. Whereas with the do while loop, the compiler is going to compile it so that this runs at least once, then the condition gets checked, and if the condition is true, then it's going to keep repeating. So a do while loop does its contents at least once, definitely. And I've said that many times, but this is the only difference between a while loop and a do while loop. This way, we don't have to have getInt in 2 places. The downside of this is that we don't get a different error message. We don't get a different message when the condition isn't met. It's the same message each time. And let's just see how that works. /do while. Please enter a number less than or equal to 8. Let's give it 10 and be difficult. So, here we can see it's asked us for the exact same prompt again. Because the program started, it did this thing once, then it checked the condition was true, so it did it again. And that's how the do while loop works. And as we can see here, we have a different error message when we use while too. We have a please try again. But with do while, it's repeating the exact same code again. So it's only running this code. So now if we do give it obviously a correct value, it is going to break out of that loop and give us thank you. And so that is essentially all of the control flow that we're going to use in C. If statements, which can be chained together or can be stacked on top of each other. Using else as well to catch when a condition isn't met and then go to the next condition. We've talked about switch statements, which compare an input or compare a variable to a specific set of cases that are possible for that value. We've then talked about while loops in some great depth and how for loops and do while loops are just simplifications of the primitive while loop. And on that point, are there any questions about any of the programs we've just been through? Because we've just been through about 9 different programs. No. Okay, that's great. Thank you.
The final note to leave on today is I mentioned that the deadline for PSET 1 is next Tuesday, which it is. Just to give you some idea about how we're going to mark that. What we're going to do is we're going to give one-to-one marking feedback to you. So once you've submitted your work, what we will do is we will check it. Myself and the other teaching fellows will check it, and then we will sit with you one-to-one during the workshops and give you feedback on your program. Tell you how it went. We are not going to score it. We are not going to give you something that you will look at just to give you a general idea of what we think. We think the feedback one-to-one is going to be more valuable than just a score. Okay? So that was week 4. That was lecture 0. Thank you all for coming.